Clouds. We see them every day, but what do we really know about them? Made up of tiny droplets, they are unpredictable. Although meteorologists are able to find out about the highs and lows heading our way, it's still hard to accurately predict extreme weather events, such as heavy rains that cause flooding. To compensate for this lack of information, a team of researchers has settled a research campaign in Ardèche, a hilly region in the south of France. They're hoping to provide additional information for weather forecasting models.
When we observe our planet from satellites, it's very difficult to establish the water vapor content within the first few kilometers of the atmosphere, and the first 3 kilometers in particular. However, 80% of the water, in the form of vapor, is to be found in these first 3 kilometers of the atmosphere, because it's there that all the atmospheric processes take place.
Patrick Chazette is a climatologist. To unravel the mysteries of this part of the atmosphere, he uses a very precious instrument, a lidar. A lidar, first and foremost, is a powerful laser beam which is emitted vertically. Up in the sky, it's blocked by clouds or particles. Using a telescope, we can determine the altitude at which the laser is absorbed.
The laser beam goes up into the atmosphere. You can see it here. There you are. The laser beam is pulsed. It will interact with molecules in the air, aerosols and clouds, and then it will come back down to the receiving system.
Patrick has a particular interest in cumulonimbus clouds. They extend upwards and are particularly unstable.
When these clouds release enough energy, it creates convection. Convection is in fact air, which is drawn up to a high altitude and forms towering cumulonimbus clouds, which will rise up into the upper atmosphere. The aim of LIDAR is to measure the water vapor content before the precipitation process, before the formation of these large clouds, so that the data can be integrated into the model and we can predict the formation of these clouds.
By the way, the LIDAR has recorded the passage of a cumulonimbus cloud, bringing with it rain and thunderstorms. As soon as it is recorded, the information is immediately analyzed.
At the top, we have the direct signal, and here we can see the various aerosols and clouds that have passed over the LIDAR during the last 2 days. At the bottom, we have the humidity, which has given rise to these storm systems. At the medium altitudes, we can see a layer of desert dust, which brought tropical humidity with it, which probably condensed to form these storm systems.
The LIDAR data will make it possible to model these extreme episodes better and to improve forecasts.
A model with a resolution of around 1 kilometer has to be supplied with data that is also high resolution, especially the vertical resolution. The LIDAR technique makes it possible to provide this data. It's really a combination of observation and modeling, which will improve our knowledge of the place in which rain is going to fall and the place in which there's a risk of flooding.
And to provide this accurate information, this LIDAR must be carefully calibrated. At the moment, it's still in the adjustment phase. The team compares its measurements with other data, such as that from the radiosondes, small measuring devices attached to helium balloons that are launched every day, which the researchers hope will be similar to that from the LIDAR.
As it's going up, a measurement will be taken underneath the balloon. When it gets to about 20,000 meters, or maybe even before that, the balloon will explode. The sensor will be carried back down under a parachute and will continue to gather data during the descent. They're used to measure temperature, humidity, and atmospheric pressure.
And to gather even more measurements, the team is even going directly in the sky. They use 3 slightly modified microlights, equipped with sensors, a computer, and another pre-configured LIDAR. But the ground-based LIDAR can provide another interesting piece of information, the isotopic composition of water, crucial information for a better understanding of clouds.
Knowing about the isotopes in water allows us to know about the history, in fact, of that water in the atmosphere, where the water that precipitates in a given place came from, and therefore, its history. Have there been any disruptions in the transport of this water? Has this water, for example, condensed, precipitated, re-evaporated, etc.? So we have that kind of information.
To go even further, Another experiment is even collecting tiny pieces of clouds, thanks to this droplet trap fixed to an ultralight.
The droplets hit the cones and then fall due to gravity to the bottom here, where we have a channel that collects the water. Below that, there's a bottle which holds all the water that has been caught.
The idea is to get a better understanding of the way clouds form, and in particular, the role of aerosols, the particles necessary for condensation.
The cloud is made up of suspended water droplets, and each droplet is formed by the condensation of water around an aerosol, a suspended particle. What we don't know is why some aerosols succeed in condensing water, while others don't.
Thanks to this field campaign, scientists are learning a little more about what's going on above our heads. Next year, the team will install several networked lidars around the Mediterranean Sea to study intense weather events. The aim is to help the authorities make decisions, such as launching evacuation operations, for example, and preventing natural disasters from turning into human tragedies. Lidars will also be able to anticipate heat waves. In the face of climate change, this technology could soon become essential.